In this video, we'll continue the one-way analysis of variance that was started in the previous video. We've got to the stage where we'd fitted the analysis of variance model using the LM, linear model function, created a summary of the fitted model, and looked at confidence intervals for the model parameters. So what we'll move on to next is to consider the model diagnostics. So here we're taking a look at the residuals for the model, and the residuals are the difference between our observed data and the values that the model is predicting at those particular settings, and we're comparing those against the fitted values for the model to see if there are any systematic patterns in the data. So what we do here is we're going to create a data frame, plant.mod. So we use the function data frame, and we're going to store various bits of information here. So first of all, the actual fitted values for the model. So we'll call that column fitted, and we make use of the function fitted. We put in the name of our model, plant.mod1. So what that will do is extract the fitted values from our model fit. We then create a column residuals, and we use the function resid and our model plant.mod1. So this will extract the residuals for the fitted model. And lastly, which treatment group they correspond to. So what we do here is to extract the column from our original data set, plant.df$group, which tells us which group each of those fitted values and residuals corresponds to. So we submit that command, and we've got our residuals saved here. So we make use of the function ggplot, tell it the data frame that we're going to use is plant.mod, which is the data frame we just created. On the x-axis we're going to have the fitted values, on the y-axis the model residuals, and then lastly we want to indicate which treatment group the fitted values and residual pairs correspond to by mapping the color aesthetic to the treatment column. Then lastly we specify that it's a point geom we're interested in because we're looking at a scatter plot. So we look at the graph here. We can see that there are three fitted values corresponding to each of the groups, and that's because of the way that the model is specified, where we're estimating the average weight for each of the three groups. We can see that the variability differs across those three treatment groups, which might suggest it's worth considering possibly a transformation or some other approach to handle the fact that we don't have constant variance. So far we've used the LM function, so the linear model approach, to looking at analysis of variance model. Alternatively, there's a function AOV, which is slightly more restrictive, but allows us to fit analysis of variance models and produce some specific outputs of interest. So we have our plant.mod2 as we're creating another model, and we make use of the AOV function, and what we'll notice is that the information in the arguments is the same as if we were fitting the linear model LM. We specify a formula first. Weight is our y value that we're trying to model, and group is the only x variable, independent variable that we've got in this model. Submit that command. No response from R indicates that there aren't any errors or warnings or any output to produce. And then, just like with the linear model, we can make use of the summary function that produces a different summary because we've got an analysis of variance model here. So here we can see an analysis of variance table, which we might be more likely to expect given that we're fitting an analysis of variance model. We can see the single star indicates that there's some evidence of a difference between the three treatment groups. So as we are following the analysis of variance model approach, a couple more things we might be interested in extracting from our fitted model. Model tables is a function that allows us to get a table of the averages for the groups, so we can see how they are in relation to each other. And then lastly, there's a function Tukey HSD, which allows us to extract the Tukey honest significant differences from this fitted analysis of variance model. So these confidence intervals against the differences between all of the pairs of treatments have a p-value that's adjusted because we're undertaking a multiple comparison analysis here.